All right, folks, welcome back. We are going to continue our work in Chapter 6, Exponential and Logarithmic Functions. Today, we're specifically looking in Section 6.2, Properties of Logarithms. So the first thing I'm going to do is cover some algebraic properties of logarithmic functions, and there are three of them: product rule, quotient rule, and power rule. And I have the symbolic version here, and I'll just show you a quick numeric example to illustrate that. So let's take a look at the first one. The log base b of the product u and w equals the log base b of u plus the log base b of w. So let's look at a numeric example of that. Let's say I have the log base 2 of the number 10. Well, I know that the number 10 equals 2 times 5. So I could rewrite this as log base 2 of 2 plus log base 2 of 5. And if I wanted to simplify that further, I know the log base 2 of 2 is just 1, so I could rewrite this as 1 plus log base 2 of 5. All right, next example is the quotient rule. Log base b of the quotient u and w is equal to log base b of u minus log base b of w. So let's take a look at this one. How about an example here like the log base 7 of the number 5. Well, 5 I could rewrite as 50. Cleaner alert, you don't need to worry about that. 50 divided by 10. So I could rewrite this as the log base 7 of 50 minus the log base 7 of 10. Okay, so there's the quotient rule illustrated for you. Here I didn't necessarily pick any nice numbers. I'm just picking numbers 5 and 7 and showing you one way that this property works. And one thing that's important to note here is for both of these properties, they work forwards and backwards. So if you have an expression that looks like this, the sum of two logs that are the same base, you can rewrite it in a simpler form like this, where the product, it's the log base b of the product u and w. One thing that might help you remember these two rules, the log of a product is the sum of the logs, and the log of a quotient is the difference of the logs, if you're looking for another way to remember that. Let's move on now. Log base b of u to the w, that's the power rule. Basically, it kind of looks like, and I really don't want to say this, but a lot of students find this helpful. It kind of looks like you're factoring out the exponent. It's not really what happens in the background. You're not factoring out the exponent, but you can take that exponent out and rewrite it as w times log base b of u. So let's look at a numeric example here. What if I have, we'll say the log base 3 of, we'll pick a number like, how about 16? Well, 16 is 2 to the 4th power. So I could rewrite this as log base 3 of 2 to the 4th power. Now I can take that exponent out and now use it as a multiplier. It's 4 times log base 3 of 2. If you're interested in a little challenge, I'd encourage you to think about how the product rule and the log rule relate to each other. And let me give you an example. What if I have the log of 3 times 3? Well, that's really the log of 3 squared, and based on the product rule, we could rewrite that as log of 3 plus log of 3, and then that further simplifies just to 2 times the log of 3. So I'm just trying to show you a connection there between the first rule, the product rule, and the power rule. Okay, let's move on. We've got a couple different rules here. Now these are change of base formulas, so when would you use these? Well, let's say you're given an exponential a to the x, but you want to change it to base b. There's a formula for that. Okay, a to the x equals b to the x times log base b of a. And that is not a formula that I'm going to force you to remember because it's pretty limited application. The one I'm going to show you a base 10 example of what that looks like, and then a base e example, because those are the two bases we use most often. So if we have a to the x and we want to rewrite that in base 10, well, b equals 10, and that's going to be x times log base 10 of a. So that's how you would change an exponential from base a to base 10. When we start doing some examples here in a few minutes, these formulas will make a little more sense. How about base e? What if I have a to the x and I want to change it to base e? Well, the base e raised to the x times the natural log of a. So that's how you would change a to the x into base e. This formula right here, if you continue your mathematical studies and move on to calculus, you'll find that that formula is pretty helpful because the calculus of e is a whole lot easier than the calculus of a. But that's enough about e and a right now. Let's move on and look at log base a of x. How can you change base if you want to change from base a to base b? Well, let's look here at an example involving base 10. If I have the log base a of x and I want to change that to base 10, that's the log of x, log base 10 of x, divided by the log base 10 of a. So why is this formula important? Well, back in the day, prior to a log base key on the calculator, this was how you would change from a base of a to a base of 10, the common base. And a couple of you, I think I've already showed you that on your calculator because you have a little bit older calculators like TI-80, 83, or an old 84. And I'll show you an example of that once I get going into the examples here. Okay, last but not least here, if I want to change the log base a of x into base e, that will be the natural log of x divided by the natural log of a. And remember, for all these examples, a and b are constants. They're not changing. So the a and b there, those are constants. X is still a variable. Same thing here. A and b, those are constants. Those are things we know. But x is a variable. All right, so let's go ahead and take a look at how we're going to apply these rules. The first problem here says expand the following using the properties of logarithms and then simplify. Assume when necessary that all quantities represent positive real numbers. Why do we have that last statement in there about assume that all quantities represent positive real numbers? Because we can't have a negative input or a zero input to a logarithmic function. Okay, so first thing we have here is the log base 3 of x divided by 27. First thing that jumps out at me is I'm thinking quotient rule because I have a quotient there. So I'm going to rewrite that as the log base 3 of x minus the log base 3 of 27. And notice how it says this word that students like to ignore sometimes. It says simplify. So I kind of now need to look at this a little further and see if there's anything I could simplify here. Well, I know that 3 cubed is 27. So that means this guy right here simplifies to 3. And my final answer is going to be the log base 3 of x minus 3. There's our final answer for part A. All right, part B. I'm going to pick up the speed here a little bit. If there's anything worth discussing, I'll slow it down. All right, folks, on that one, hopefully you noticed the first thing I used was the product rule. So I took the product of 16 and x squared and split that up into the sum of two logs. Then I simplified log base 4 of 16 to 2 because 4 squared is 16. And then I used the power rule. I took the exponent of 2 out as a multiplier out in front of log base 4 of x. All right, let's take a look at example C now. First thing I'll mention here is just some notation. The thing that we're taking the natural log of is this entire quantity, 3e over x squared. So, and the way that's written is sometimes confusing for students, so I'm going to rewrite it. Oh, not lm. That would not be, that would be ln. Okay, so the natural log of, it's the entire quantity, 3e over x squared. That is what is being squared. You're taking the natural log of that. All right, so let's go ahead and speed through this. All right, again, folks, in that one we used a veritable smorgasbord of logarithmic properties to find this final answer. We used the power rule, we used the product rule, and we used the quotient rule. All right, folks, let's move on to part D here. First thing I'm going to do is simplify what's written here before I start using properties of logarithms. So I'm going to take the square root of everything that's in here inside this expression. So this is going to end up being the log of, well, the square root of 100 is 10. And then the square root of x cubed is going to be x to the 3/2 power. The square root of y, I'm going to rewrite that as y to the 1/2 power. And then the square root of z to the 4th, well, that's going to be z squared. So I just rewrote that to take care of the square root symbol up front. From now on, throughout the rest of this problem, let's use properties of logarithms. All right, folks, there you have it. There's the answer to part D. And actually, it would be marked wrong in WebAssign because there's a part I didn't simplify here. The log base 10 of 10 is 1. So I can rewrite this as 1. So final answer is going to be 1 plus 3/2 log x minus 1/2 log y minus 2 log z. And I'm not sure if you slowed the video down or not, but you watched. Make sure that you see that both of these terms are subtracted because they are both in your denominator. And that's a little rule of thumb. Anything in your denominator better be subtracted in the expression. All right, let's move on to part E here. So I included this example for one reason, and that was to try and trick you. So do not write down what I'm about to show you. Log base 3 of x squared minus 1 does not equal log base 3 of x squared minus log base 3 of 1. And students will do this all the time, and this is one of those things where I want you to slow down and think about this. Do not confuse this right here for any of the rules that we have above. There's none of these rules that show a difference inside the parentheses of what you're taking the logarithm of. So this is totally wrong. Don't do it. What I'd rather you do is rewrite it. Think about x squared minus 1 in there, and can you turn x squared minus 1 either into a product, a quotient, or a power? And I think if you think about it long enough, hopefully you can rewrite it as a product because x squared minus 1 is the difference between two perfect squares. So I can rewrite this as a log base 3 of the quantity x minus 1 times x plus 1. Now I have a product. I can use the product rule and rewrite this as log base 3 of x minus 1 plus log base 3 of x plus 1. And that's it, folks. You can't simplify that one any further. All right, let's move on. A couple more to go here. This next one is got a product rule in there as well as a power rule. So I'm going to whip this one out here for you pretty quick. That one was pretty straightforward. Hopefully you followed along there. Now let's take a look at example G here. I got the log base 2 of this monster, 256 divided by x squared plus 4. So first thing I see is I have a quotient. So I'm going to use the quotient rule here and rewrite this as the log base 2 of 256 minus the log base 2 of x squared plus 4. And 256 is one of those numbers that should kind of resonate with you a little bit. 2 to the 8th power is 256. So we can simplify that to 8. So this whole thing simplifies to 8 minus the log base 2 of x squared plus 4. Now I have a question for you. Can you simplify the log base 2 of the quantity x squared plus 4? The answer is no. Because inside the parentheses there, x squared plus 4, I cannot rewrite that as a product. I cannot rewrite that as a quotient. I cannot rewrite that as a power. So that right there is its final, most simplified form. All right, last one here before we flip to page 2. I got the log of root 2, holy cow, that's a strange base, of 8 times x cubed. So let's take a look at what we got here. There you have it, folks. Final answer here for part H is 6 plus 3 times the log base root 2 of x. And hopefully you follow along with my little work there at the bottom to show you why the log base root 2 of 8 is 6. All right, folks, let's shut it down and look at page 2.